This time around, we're talking about linear regression. This is a step up from scatter plots. Scatter plots set the stage for us to determine whether or not there is a pattern. Linear regression allows us to recognize that pattern and possibly even use it to make predictions. This whole entire unit is about exploring relationships between variables. But again, they have to be specific types of variables in order for linear regression to work. They have to be quantitative, both of them. Now, what we're doing here is we are trying to fit a linear model to our data. A linear model is really, it's just what you would expect. It is an equation of a straight line through the data. The emphasis here is on a straight line. Now, the thing with this, it is a model. Your points are not going to be perfect. Your line is not going to go through all of the points, and really your goal isn't even to try to go through as many points as possible. Your goal is to try to have a model that best fits the data and to help us to figure out what type of relationship exists between our variables. Now, no matter how we draw the line, you are going to have points above and below, and we use our line to make predictions. Now, we've talked about y bar. This is called y hat. When you have a little almost caret drawn above a variable, we actually do call those hats. And that tells us a value that we predict. Bar is an average of values that we have seen. Y hat is a predicted value for a specific, for a specific x value. Now, when we make predictions, we typically are going to be making errors on those predictions. And the difference between an observed value and its predicted value, that's our residual. Sometimes people think about that as an error. How far off are you? But in the world of statistics, we call those residuals. The residual is a very easy equation to think about. It is just starting with your observation, subtracting from that your prediction, and that's your residual. And you can see here that the notation for that is y minus y hat. Now, you want to be a little bit careful with this. You always want to remember which value comes first. The observed comes first, the predicted comes second. That means that if your residual is negative, then that means that your predicted value was too high. You overestimated. If your residual is positive, that means the observed value was the greater one. Your predicted value was too low. That's your underestimate. It's a very hard thing for some reason to keep straight. But just remember that what is important in all of this is your observations. The observations are known. The predicted comes secondary. So it's always observed minus predicted. Now we take all of these residuals, and in finding them, our line of best fit is an attempt to minimize the residuals, and not just minimize them, but minimize the squares of those residuals. So what we do is we take our lines and we calculate all sorts of different ways to find what the residuals, the observed minus expected, would have been, and we square those because we're not interested in a positive or a negative error, we just want total error. And in squaring that, we take care of that very simply. The line of best fit minimizes all of those residuals squared. Now here's an interesting thing to kind of take note of. If we move a standard deviation away from the mean in x, this is where our correlation coefficient comes from. Moving one standard deviation away from the x moves us r, your correlation coefficient, standard deviations away from the mean in y. It is not a linear fit. It is not one step in y is one step in x. If you take 2 standard deviations away in x, we're taking 2 times r standard deviations away from the y. And we're always talking about moving it away from the mean. And an interesting thing, something that you will note in the text, is that there's one point that we can guarantee is going to be on our line of best fit. And that point is our average of the x coordinates that we have observed and the average of the y coordinates that we have observed. So x bar, y bar is guaranteed to be on our line of best fit. That's our central. And again, moving one standard deviation away in either direction in x moves you r standard deviations away from the mean in the y direction. Now remember, r itself cannot be bigger than 1, either from -1 to +1. So what this tells us is that your y predictions are going to be closer to the mean than its corresponding x was. You're going to have more variation in your x than you're going to have in your y. A standard deviation is a standard deviation. But if you are one standard deviation away in the x, you have got to be one or fewer standard deviations away in the y. Now, this is called a regression to the mean. This is a extremely important property of our linear model. It is the whole purpose of this, and that's why sometimes we don't refer to it as a least squares line or a line of best fit. Sometimes I just call it a regression line. Now that regression line is modeled by the equation y hat, your predicted value, is equal to b sub naught or b sub 0, a starting value, plus b sub 1, which is your slope, times x. So x is going to be any value that you want to predict. Y hat is the value that comes off of that. Now, those are solutions to your predicted values. And in all honesty, when we are in class, we're not going to be using x's and y's. We're going to be putting full words in there. We might say that the height hat, or a height prediction, is equal to initial height plus your slope times however many years you've been watching or days you've been watching something grow. And so you would actually have words in place of y and x. But no matter what, we always put a hat over your predicted values. And this is saying that our predicted values follow a straight line. It's not saying that our observed values will, but our predicted values should. So again, b sub 1 is your slope, b sub naught is your intercept. Now, the slope tells us how rapidly, and that's supposed to be y hat changes with respect to x. So your slope is how quickly your predicted values of y change with respect to x, whereas b sub naught is the y-intercept. So some of these things aren't going to change. We have changed the order here, and the simple reason is when we modify regression, sometimes we do that by simply tacking on additional variables at the end, and it just makes it easier for statisticians to deal with. So we're going to start here with our slope formula. The slope formula for our b sub 1 talks about the correlation coefficient r and your standard deviation of both the x coordinates and the y coordinates. Now, if you recall from algebra, slope is rise over run, delta y over delta x. Therefore, when we do this, it is the standard deviation of y divided by the standard deviation of x. So if you were to put all of your coordinates into a list in your calculator and perform a 1-var stats or calculate all your statistics on it, you would take the standard deviation of your y values and divide it by the standard deviation of your x values. You kind of put that into perspective of a sampling distribution. We don't need to worry about the sample size themselves because our points, our pairs, should have the same sample size. So to divide by the square root of the sample size, those two values would actually cancel each other out. And r, your correlation coefficient, basically tells you the strength of the relationship between the two. So a less strong relationship is going to have a smaller slope. And you must remember that just like in algebra, your slope is always in units of y per unit of x. So it's still change in y over change in x. Now our intercept formula requires the use of that slope. So your intercept formula for b sub naught is just really taking your predicted equation of y hat equals b sub 0 plus b1 times x and solves it for that b sub 0. But like I told you, we only know of one particular point that is on every regression formula, and that is, or on every regression line, and that is your x bar, y bar, the average of each, which is why whenever you're trying to find an intercept, you use your knowns. You use the things that you know to be on the line. You know x bar and y bar are on the line, so you substitute those in. And we have previously found the slope using our correlation coefficient and our standard deviations of the x and y. Now, our intercept is a y coordinate, so please recall it's always in units of y. So back to the residuals. Your linear model is always assuming that the variables are in a perfect straight line. And the residuals capture the portion of the data that hasn't been modeled, that's not captured into your equation. Your data, just like we said that our error, our residual, is our observed minus expected, if we solve that instead for our observed, that's our data. The data is the model, the predicted, plus the residual. And so this is the other way around. It's your observed minus expected. Your residual is your data minus the model. And we put that into symbols with E. E is in this case standing for residual. We can't use R, that's a regression. So your error is y minus y hat, your observed value minus your predicted value. Now, in order to do regression, we can't just do it any old time. So it's kind of interesting how it cycles back through itself for these conditions. The main conditions still carry over from what we needed to do any type of correlation. And that is that the variables themselves have to be quantitative. There's your quantitative variable condition. When we are looking at the original scatter plot, that data has to be straight enough, so it has to look linear. We can't see any obvious curves or clusters, and we can't have any obvious outliers. That's our outlier condition. And those really, it's pointless to even kind of go more into those because the names say it all. However, that's just on the scatter plot of the data itself. Once we do that, we take our data, we perform the regression, but then we actually have to graph the residuals. The residuals themselves come in their own scatter plot. So here's scatter plot number 2. After we fit the regression model, you look at your residuals and you really hope to see absolutely nothing. I don't mean you don't want to see any points, but you don't want to see any patterns. You definitely don't want to see any curves, and you don't want to see something that's really kind of weird. And this is called your equal variance assumption. And we check it by this funny little thing called does the plot thicken condition. And what that means is as you move from one side of your graph left to right to the other, you do not have a thickening of the points. It doesn't look like a funnel turned on its side, where you might have a spread of data in the y on your lower values of x and very few data on the right in the higher values of x. You don't want to see a sideways hurricane. It's going to look weird. That's your does your plot thicken condition, and that only is determined off of the residuals. So there's that other value that you get from doing regression, and that is R². And that is, in effect, squaring your correlation coefficient. This is extremely key in telling us how well the model fits. It's no longer just telling us, okay, whether it's positive or negative, but it also gives us some very important data. What this tells us is it tells us the fraction of the data's variance accounted for by the model. What that means is, for example, let's say our R² was 85 or 0.85. That would mean 85% of the variation in y is accounted for by the change in x. And therefore, if we look at the opposite end of that, 1 minus R², that's the amount of variance left in your residuals. That's the amount of change in your y values that is attributed to something other than a change in your x values. Now, no matter what, your regression analysis, and this is not the description of the scatter plot anymore, this is your regression analysis. So if you return a regression equation, you must include the R² value. Your R² value tells you how much of, again, the change in y is accounted for by the change in x. And an R² of 0 means that there is no relationship. You cannot fit, your model itself is not capturing any change. All of the change is left in the residuals. And so you must always interpret that. And I don't mean respond with what the R² value is. You must turn around and say, okay, based on my model, 75% of the increase in calories is due to the increase in protein. You have to be able to put that back into context. Checking your residuals allows you to see whether or not your R² makes sense. So these guys go hand in hand. When you do your regression, check your slope and your intercept, interpret what they mean, interpret what your R² means, and be sure to check your regression model and check your scatter plot of your residuals. Because all of this is about variation. R² is measuring those, the success of the regression model, and you want to make sure that you include that. Now, in your does the plot thicken condition, this is one of those things that you have to continuously go through and check when you're making your assumptions. Because sometimes we will be modifying our equations to try to get it to better fit the data if specifically our does the plot thicken condition does not hold true, or if we see a pattern in the residuals. The residuals should always show an equal spread when you go through it. So you want to make sure that you check for those spreads in the residuals. That's your does the plot thicken. Okay, now why do we do all of this? We do all this to try to make predictions about the natural world, or about or the unnatural world, depending upon what it is. But the thing is that our statistics themselves are not pulled from thin air. They're based on our data that we have collected. And this data should make sense. You shouldn't be expecting, oh, I dropped my book, and then all of a sudden you're seeing that your book flies upward in the air. You shouldn't predict that 2 seconds after somebody drops a penny out of the window, that penny is now higher. You have to check your results to make sure they make sense. It's not supposed to be ridiculous. And if there is something that is weird, maybe you did discover something new and interesting, or maybe you made a mistake. So always go back to the context. Think about your coefficients, think about what it means. Ask yourself if it makes sense, because sometimes your regression model will only make sense within a certain window. It won't make sense, for example, next to the intercept. Might not make sense far outside of the span of data that we've actually collected. So you have to make sure you look at your data, you look at your coefficients, and make sure that they do not seem unreasonable. Be very careful of extraordinary points. Now, those can be any point that is very far from the linear pattern, either in the x direction or in the y direction. Both of those values have different types of effects on the graph. Both of those tend to be outliers. And remember, while our regression analysis and while our correlation coefficient is immune to changes in scale, it is not immune to outliers. And probably the biggest thing that you need to be careful about this is not to extrapolate beyond the data that you've collected at hand. Now, depending upon what the purpose of your experiment or your model is, different types of limits are imposed. Sometimes people say that whether you're trying to make a prediction outside of any observed data, even if you go 1 or 2 units beyond the data that you've collected, they might classify that as extrapolation. Depending upon the severity and the importance of what you're doing, you have to be very, very careful about that. Other people might use a proportion looking at the range of the data that you've collected and saying, okay, well, we can go, let's say maybe 10 or 15% beyond that. But you have to be realistic. You have to understand that if you go beyond the data that you've collected, you're actually trying to make predictions into the future. And we are not fortune tellers. So be very, very careful with that. Be careful with anybody's interpretations that come from that. But whatever you do, when you're looking at those values for your regression line, do not base your values, do not base your belief in your model on your R-squared alone. We're going to be seeing as we look further into re-expressing our models that there can be several models that give us very similar R-squares. We've also talked about the importance of outliers, and an outlier can make a very small R-squared appear very large, or a very large one appear small. So you've got to be very careful. Again, interpret what you are thinking about, put it into perspective, put it into context to see if your model makes sense. It's not just about R-squared. It's a balancing. Remember, statistics is an art. It is not a black and white answer. So be very careful when we go forward.